imagine, just for a second, that you hold the ultimate power. Like the power to go back and rewrite your absolute biggest regret.
Right.
I mean, we all have one, right? That one pivotal moment you would give literally anything to just do over. So you step into the machine, you punch in the date, you arrive right at that critical moment, and right as you reach out to change history, you trip.
Oh, yeah.
Or, the door locks. Or you suddenly just lose your voice. You try again, and a completely bizarre, entirely different coincidence stopped you.
Yep.
It turns out the laws of physics simply won't let you change it. Okay, let's unpack this, because today we are taking a deep dive into the fundamental nature of time, causality, and, well, the mind-bending physics of altering the past.
It is an incredibly fascinating journey, and we have a very specific stack of sources guiding us today for this deep dive.
Yeah, we've got a lot of ground to cover.
We really do. We want to understand exactly how theoretical physics attempts to solve the ultimate headache of time travel, which is, of course, the paradox.
Right, the stuff that breaks your brain.
Yeah, exactly. We'll be synthesizing a comprehensive Grokipedia breakdown of the Novikov Self-Consistency Principle, some deeply complex theoretical papers on post-selected closed timelike curves by Seth Lloyd, notes on Professor Ronald Mallett's real-world laser time machine. Or, well, theoretical machine, I should say.
Still so cool, though.
Oh, absolutely. And we'll even look at the mathematical architecture of 5D metric spaces. Our mission here is to figure out how these theories clash and to explore the logical beauty of a single, unalterable timeline versus, an infinite multiverse.
I really appreciate that we are grounding this in actual science. I mean, we're taking time travel completely out of the realm of, science fiction fantasies and looking at the rigorous academic physics.
Right, the real math.
Because the math actually says it's possible, which is just wild to me.
All right.
But before we get into paradoxes and jammed timelines, we have to establish how you even travel back in time in the first place. I mean, you can't just throw a DeLorean into reverse.
Unfortunately not, no.
The sources talk about CTCs a lot.
Yeah.
What are those?
Yes, so closed timelike curves. To really understand a CTC, you have to look at how Albert Einstein fundamentally changed our understanding of reality with general relativity.
Okay, lead on me.
So before Einstein, we kind of thought of gravity just as this magnetic-like pull. But Einstein showed us that gravity is actually the physical warping of space and time by mass and energy.
Right, like the classic bowling ball and a trampoline analogy. You
Yeah.
put the heavy ball in the middle, it creates a dip, and things naturally roll into it.
Exactly. That's the perfect way to visualize it. But general relativity mathematically allows for paths in space-time that warp so extremely, the dip, as you call it, actually folds over and loops back onto itself.
Wait, really? It just folds completely over?
Yeah. Returning to an earlier physical point in time, that loop is what we call a closed timelike curve. It's a localized path where the future circles back to become the past.
So it's like an actual physical path you can traverse. But instead of just walking from New York to London through space, you're walking from Friday back to Thursday through time.
That's the idea, yeah. The famous mathematician Kurt Gödel actually proposed a rotating universe model back in 1949, where these curves are just a natural, ubiquitous feature of the cosmos.
Wow, 1949.
Right. But since we don't actually live in a rapidly rotating universe, physicists have had to get a little creative. This brings us to Ronald Mallett, who is working on theoretical models to create a CTC artificially using light.
And this isn't just a thought experiment for him, right? He's trying to build the foundations of a real physical machine.
Yeah.
But, I mean, how do you use light to bend time? That sounds impossible.
Well, it comes down to Einstein's most famous equation, E_mc², which tells us that energy and mass are fundamentally the exact same thing.
Right, okay.
Because a massive object like a black hole can warp space-time, a sufficiently intense concentration of energy can do the exact same thing. Mallett proposes using a circulating cylinder of incredibly intense, continuous laser light.
So by spinning this intense light,
Yeah.
what exactly is happening to the space inside the cylinder?
The circulating energy creates a sort of gravitational vortex. Think of space-time like a thick cup of coffee.
Okay, I like coffee.
Right. So if you take a spoon and stir it really fast, the coffee swirls around the spoon. In astrophysics, this is called frame dragging.
Frame dragging, got it.
Yeah, the spinning lasers theoretically drag the fabric of space along with them. And since space and time are inextricably woven together as spacetime, twisting space so severely means time gets twisted right along with it.
Until it folds.
Exactly, eventually folding into a closed loop.
That is just wild. And this is where the 5D metric spaces from our sources come in, right?
Right.
Because I was looking at that and trying to figure out why on earth we need a fifth dimension to make sense of Mallett's swirling laser coffee.
Precisely. In standard four-dimensional physics, so that's 3 dimensions of space, and one of time space-time into a literal knot creates immense mathematical contradictions, specifically regarding electromagnetism and gravity.
They just don't play nice together.
Not at all. But if you model this in a 5D metric space, which essentially adds an extra unseeable spatial dimension, you give the mathematics a lot more room to breathe, so to speak.
Oh, I see. It's like trying to draw a cube on a flat piece of paper. It looks distorted and messy, but if you pop it out into actual 3D space, the geometry works perfectly.
That is a brilliant way to put it, honestly. Yes, the 5D metric provides the mathematical degrees of freedom required for these loops to exist without violating the standard constraints of our physical universe.
Okay, but, I mean, even if the math works in 5 dimensions, and even if Mallett can stir spacetime with lasers, doesn't the sheer existence of a CTC inherently break the logic of reality?
How do you mean?
Well, if I can loop back, I can mess with the loop. It's like writing a software script that is designed to actively hunt down and delete the exact line of code that triggered the script in the first place.
I see where you're going.
Right. The moment it succeeds, the script never runs, meaning the code is never deleted, meaning the script runs. The system should just blue screen and crash entirely.
And physicists absolutely despise logical crashes. What you've just articulated is the classic grandfather paradox.
Right, exactly.
If a CTC exists, what stops a time traveler from going back and preventing their own existence by, say, assassinating their own grandfather before their parent is even conceived?
Right, you succeed, you're never born, you never travel back, your grandfather lives, you're born. It's just a fatal causality loop.
Exactly. To study this without all the messy variables of human choices and grandfathers, theoretical physicists stripped it down to a purely mechanical model. They call it the billiard ball thought experiment.
Okay, let's hear it.
Imagine a billiard ball rolling across a table toward a wormhole, which acts as our CTC. It enters the wormhole, travels back in time, and exits a second wormhole positioned right in the path of its past self.
Oh, I can see where this is going.
Yep, it collides with its past self, knocking it completely off course so it never enters the wormhole in the first place.
Meaning the ball never went back in time to knock itself off course. Meaning it does enter the wormhole, we're right back to the blue screen of death.
Exactly. Classical physics demands a deterministic, unbreakable cause and effect chain. The billiard ball experiment isolates how CTCs threaten the very foundation of causality. I mean, how can the universe continue to function if its own history fundamentally contradicts itself?
And this is where we have to introduce Russian astrophysicist Igor Novikov. Because in 1989, he introduced the Novikov Self-Consistency Principle. And it honestly might be the most elegant, if not slightly terrifying, solution to this entire problem.
It really acts as the ultimate cosmic rulebook for a single timeline. Novikov posited that in a universe where CTCs exist, the laws of physics dictate that the probability of any paradox-inducing event is exactly zero.
Zero.
Zero. The universe will only ever admit globally self-consistent solutions.
But wait, how does math enforce a zero probability on a physical action? Like if I have a gun and I point it at my grandfather, how does a mathematical principle physically stop my finger from pulling the trigger?
This is where we have to look really closely at the classical mechanics along a CTC. Novikov, working alongside other physics heavyweights like Kip Thorne, analyzed the trajectories of that billiard ball.
Okay.
What's fascinating here is what the math actually showed. The contradictory scenario, the ball cleanly knocking itself away, is just not a valid solution to the physical equations of motion within that space-time geometry.
So what does the math say actually happens to the ball then?
It dictates that the ball will emerge from the wormhole on a trajectory that can only deliver a glancing blow. And here is the absolute genius of it.
Yeah.
That glancing blow perfectly nudges the past version of the ball into the wormhole at the exact precise angle needed to travel back in time and deliver that exact glancing blow.
Oh, wow. Okay, so the intervention doesn't change the past. The intervention is the cause of the past.
Exactly. The loop closes. It is flawlessly self-consistent. If you try to kill your grandfather, the complex variables of reality will physically enforce consistency.
The gun just jams.
Right. The firing pin on the gun breaks. You sneeze and miss. Or, ironically, the gunshot scares your grandfather into running down an alley where he happens to bump into your grandmother.
Wow.
The timeline is fixed, and it absorbs all interventions retroactively as part of its own history.
Okay, the logical purity of that is beautiful, but I mean, the philosophical consequence for you and me is absolutely terrifying.
It is a bit grim, yes.
It means if time travel exists in this way, we have a complete illusion of free will. You go back in time, you think you're making independent choices, you think you're fighting fate, but you are just helplessly fulfilling a deterministic loop.
It does create a profound sense of fatalism, for sure. The physics mandate that your choices were already factored into the very history you were trying to change.
It totally reminds me of the concept of the obdurate past mentioned in our sources. They specifically reference pop culture like The Terminator or 12 Monkeys.
Oh, those are great examples.
Right. In The Terminator, Kyle Reese goes back to stop Skynet, but his going back is what creates John Connor. And the leftover robotic parts from the fight are what cybernetics engineers used to invent Skynet in the first place.
Yes, exactly.
The characters think they're tearing down the future, but they are literally laying the bricks for it. The universe demands absolute, unyielding consistency.
Pop culture really captured the essence of Novikov's principle perfectly with those stories. It preserves causality without needing to invent complex rules. Everything happens once, and it flawlessly aligns.
Here's where it gets really interesting, though. Because as beautiful as Novikov's classical determinism is, we don't live in a purely classical universe.
We do not.
Once you zoom in and bring quantum mechanics into the picture, this elegant single timeline theory starts facing some serious competition. The physics titans start clashing.
They do indeed. Because quantum mechanics inherently introduces uncertainty and probability into the mix. Stephen Hawking looked at this through a quantum lens and arrived at a very, very different conclusion in 1992 with his chronology protection conjecture.
Chronology protection. It sounds like a sci-fi time police force.
It kind of operates a bit like a cosmic veto. Hawking argued that the universe actively protects its own history by making time travel physically impossible at the final hurdle. He focused heavily on quantum vacuum fluctuation.
Quantum vacuum fluctuations, what are those?
Well, even in completely empty space, on a microscopic quantum level, energy is constantly bubbling. Tiny, temporary pairs of virtual particles are constantly popping into existence and annihilating each other.
Okay, so space is never truly empty.
Right. And Hawking proposed that if a CTC, a time loop, were to start forming, these vacuum fluctuations would enter the loop. They would travel back in time, meet their past selves, and cycle through the loop again and again.
Like holding a microphone too close to a speaker. You get that screeching audio feedback loop that just builds and builds instantly.
That is a phenomenal analogy. Yes, the energy of those fluctuations would amplify to infinity in a fraction of a second. This catastrophic energy divergence would violently destroy the wormhole or the time machine before any macroscopic object, like a human or even a billiard ball, could even attempt to use it. To Hawking, physics intrinsically protects causality by slamming the door shut.
Okay, so Hawking says the door is permanently locked and, rigged with explosives. But then you have David Deutsch, who comes in around 1991 with a completely different key.
Right. Deutsch applies the many worlds interpretation of quantum mechanics. In Deutsch's model, you don't need the universe to jam your gun, and you don't need a massive quantum explosion to destroy the machine.
So what happens?
If you go back in time and change a state, like stopping your grandfather, the quantum state simply branches. You create a parallel universe.
Which is the view that Professor Ronald Mallett actually supports for his laser machine, right?
Yes, it is.
He basically argues that time travel is safe, because if you alter the past, you just spawn a brand new separate universe. Your original timeline remains completely unaffected.
That's correct, yes.
I'm going to be honest here. I kind of hate Deutsch's solution.
Oh, why is that?
Because aesthetically, functionally, it feels like a messy get-out-of-jail-free card. Oh, you created a paradox? No problem. Just spin off an entirely new, infinitely complex universe. Throw it on the cosmic pile.
I see.
It just feels so cluttered and evasive compared to Novikov. Novikov's principle feels like this brutal masterpiece of logic. The universe doesn't run away from the paradox by frantically photocopying reality. It stands its ground and demands absolute perfection from a single timeline.
I hear what you're saying about the aesthetic appeal of a single timeline, but hold on, you are looking at this heavily through a classical bias.
Fair enough.
We have to defend Deutsch here for a second, because in quantum mechanics, superpositions, particles existing in multiple states at once are entirely natural. Deutsch's mathematics don't just throw a universe on a pile to avoid the problem.
It sure sounds like an escape hatch, though.
But mathematically, it's a brilliant resolution of the wave function. Deutsch proved that you can resolve the grandfather paradox while preserving quantum states across branches without violating the fundamental rules of quantum mechanics.
Okay, I guess that makes sense.
It respects local physics. The trade-off, which you rightly point out is messy, is massive entropy.
Entropy being the informational messiness, right? The thermodynamic cost of constantly splitting these realities.
Exactly. The informational divergence of branching universes creates a massive spike in entropy. So you really have a philosophical and mathematical divide.
Choose your fighter.
Right. Do you prefer the infinite, branching, high-entropy freedom of Deutsch's multiverse, or the elegant, rigid, unbreakable choreography of Novikov's single history?
It's a tough call.
And for a long time, this was purely a debate of theoretical math. But then experimental physicists decided to actually build a simulation and test it.
Yes. You obviously can't build a real time machine and hurl a graduate student back to test it on their grandfather, but you can simulate a paradox in a quantum lab. Seth Lloyd's 2011 experiment at MIT. This completely blew my mind.
It is a landmark piece of research. Seth Lloyd and his team created a physical quantum simulator for a CTC. They sent a photon back in time. Well, specifically, they simulated sending its quantum state back a few billionths of a second.
Still counts.
Using a verifiable process called quantum teleportation.
Okay, so the photon is our microscopic time traveler, and they decided to give this photon a mission.
Figuratively speaking, yes, they built what they termed a quantum gun.
I love that name.
The experiment was designed so that the photon would travel back and attempt to, quote-unquote, kill its former self by flipping its own polarization state. If the photon started as a 1, the time-traveling version would interact with its past self and force it to flip to a 0.
The ultimate microscopic paradox. Because if it successfully flips its past self to a 0, then a 0 is what entered the time machine, which means it wouldn't have possessed the one state needed to flip it to a 0.
Precisely.
It's the billiard ball all over again, just way smaller. So they run the simulation. What actually happens?
The quantum gun misfired. Every single time.
The universe literally jammed the gun at the subatomic level.
Physically and mathematically, yes, it did. To understand how, we have to define a concept called post-selection, which was central to this PCTC model, post-selected closed timelike curves.
Okay, what does that mean?
In quantum mechanics, post-selection allows you to condition the outcome of an experiment mathematically so that it only accepts results matching a specific final state. Think of it like taking a photograph with a really messy, chaotic background and applying a mathematical filter that only allows the pixels forming the subject to resolve, throwing away everything else.
Okay, so they set the physical constraints of the experiment to only allow a closed loop. But how does that stop the photon from actually flipping?
It comes down to probability amplitudes. In quantum physics, a probability amplitude is essentially the mathematical wave that determines the likelihood of a particle being in a certain state.
Okay.
Like physical waves in a pond, these mathematical waves can amplify each other, or they can crash into each other and cancel out, which is called destructive interference.
So what did the post-selection filter do to those waves?
The nonlinear math of the post-selection actively took tiny random quantum fluctuations, basically microscopic noise, and amplified them specifically to create destructive interference against the paradox.
Okay.
The probability amplitude of the photon successfully flipping its past self literally canceled itself out. The probability became 0.
So what does this all mean, if I can try an analogy here? Earlier I talked about a rigged carnival game. But it's not just a hoop that's too small. It's like playing a highly advanced virtual reality game, and you try to shoot a target that the game's core programming literally relies on to function. No matter how perfectly you aim, the collision detection engine mathematically cannot render the bullet hitting the target.
I like this.
The code dynamically shifts the digital air pressure, bending the bullet's trajectory, because the action violates the foundational rules of the software itself.
That is a phenomenal update to the analogy. The physical laws of the system dynamically respond to the threat of a paradox. The fluctuations in the system, acting at the fundamental quantum level, serve as the strict guarantors of causality.
It is spectacularly cool, because it shows that in this specific quantum framework, Novikov was right. The photon survives. The timeline remains utterly consistent.
Exactly. And crucially, it managed to resolve the paradox while remaining in a pure quantum state, entirely avoiding the massive entropy and the chaotic branching realities required by David Deutsch's multiverse model.
You just shut it down.
Yes. Lloyd's experiment proved that physics has built-in mechanisms to enforce a single, consistent history.
We have covered a whole lot of ground here today. I mean, we started with the headache of causality loops, the blue screens of reality, and the billiard balls colliding.
We certainly did.
We saw Hawking trying to blow the time machine up with vacuum feedback, and Deutsch trying to endlessly photocopy the universe to escape the problem. But ultimately, we found Novikov's elegant, unbreakable timeline, backed up by Seth Lloyd's actual quantum simulations, proving that the universe will literally physically bend probability to jam your gun and protect its own history.
It truly forces us to completely reevaluate our relationship with time, causality, and, well, our own actions. In fact, if we connect this to the bigger picture, it might completely change how you look at your everyday life.
Wait, really? How so?
Well, if the Novikov Self-Consistency Principle dictates that the universe actively assigns a strict zero probability to paradoxes, that reality will literally amplify quantum noise to enforce consistency, consider the everyday failures or coincidences you experience.
Are you talking about the weird stuff that stops me from getting out the door on time?
Exactly. A severely jammed printer when you're rushing to print a critical document.
Oh, that happens all the time.
A missed train because your shoelace inexplicably snapped. A sudden, bizarre moment of hesitation before you cross a busy street. What if those aren't just moments of random bad luck? What if they are actually the universe's localized probability corrections?
Wait, you're saying my printer jamming could legitimately be the universe actively preventing a spacetime paradox?
It is a highly provocative thought to leave you with, isn't it? If the timeline is a single, self-correcting organism, it is constantly, invisibly pruning away impossible futures to maintain its own existence.
That is wild.
The next time you experience a massive stroke of bad luck, a bizarre delay, or a deeply frustrating failure, don't just curse your misfortune. Consider that you might be experiencing the Novikov principle in action. That bad luck might just be the universe actively preventing a microscopic temporal paradox, jamming the quantum gun and safeguarding the space-time continuum right in front of you.
I am absolutely going to use that as my excuse the next time I miss my bus. Sorry I'm late. I was just busy not unraveling the fabric of reality. Thank you for taking this deep dive with us, and we'll catch you on the next one.